Welcome to State of Simulation, the podcast all about multiphysics simulation, where we stay up to date with what's working, what's not, and what needs to change. Each episode features an open conversation with the engineers and technical leaders shaping the future of physical product development. I'm your host, Jukka Knutinen, and in today's episode, we're speaking with Dr. Çağlar Aytekin, lead AI developer at Quanscient. With over 17 years of experience in machine learning, from neural network research at Nokia to productizing AI in consumer tech, Çağlar brings a deep technical understanding of how and where AI actually works. In this episode, we dive into the role of AI and machine learning specifically in the context of physics simulation, building on Çağlar's experience leading the AI development of our multiphysics simulation software, Quanscient AllSolve. We break down techniques like physics-informed neural networks and neural surrogates, talk about the promise and pitfall of hybrid AI physics methods, and explore how large language models can assist engineers in automating the workflows. No matter your experience with the topic, this conversation is guaranteed to have something for you. Without further ado, let's get started. AI is pretty much everywhere at this point, but what we're interested in this episode is to hear that how is it currently being used in the scope of multiphysics simulation?
Right. Thanks for the question. So artificial intelligence and machine learning are basically enhancing multiphysics simulations, primarily by accelerating computations via generating neural surrogate models, as well as automating the engineering workflows and therefore optimizing the designs. So you can use it in an inverse problem setting as well. We are seeing definitely an increasing adoption of neural networks to approximate very complex physical interactions via either foundational neural network solvers or PINs, physics-informed neural networks, or some other methods. These significantly reduce the simulation time, and they actually enable a lot faster exploration of the design spaces.
Right.
So this is basically a quick overview of how people are using AI and ML in multiphysics simulations.
Could you already mentioned a couple of these techniques there, but could you go into bit into the detail of exactly what kind of techniques are being used already today?
Right. In the solver space, like now we're maybe it makes sense to divide the applications of AI in multiphysics simulations into two. One of them can be the engineering part, which has a lot more to do with generative AI and how the current LLMs or multimodal large language models can basically help the engineers during the problem forming. And the other one is the solver space. Now, we can call that simulation AI. If you're talking about the techniques regarding the simulation AI, there are basically two main techniques and the one hybrid one. One of them is the physics-informed neural networks. So these physics-informed neural networks PINs, they're basically aimed to entirely replace the classical solvers like FEM by just solving the entire thing with neural network. So how people do it is that the boundary conditions and the physics equations are given as a constraint or a loss function to the neural network. And per problem, we are actually solving for the entire output instead of using FEMs. So you can think about them as a direct replacement of the classical solvers. The other track is neural surrogates, and their a lot advanced version is the neural operators. So these kind of networks find a mapping between function spaces, and they learn from training data. So instead of replacing the classical solvers, they are learning from the outputs of the classical solvers and acting as a surrogate to classical solvers. So the downside of these, maybe we can talk about the downsides of these later, but just this is how they do it. And there are also, of course, hybrid models combining the both strength of artificial intelligence-based ones and the classical solvers. And combining the flexibility of the data-driven approaches with the prediction accuracy of the numerical methods.
So you mentioned that the physics-informed neural networks, the PINs. So if we take a closer look at those, what are the strengths and weaknesses there?
Right. Currently, PINs, to be perfectly honest, are at still a research phase. The limitations of those is, of course, the prediction accuracy of the current solvers, FEM solvers that we have, for example. But I'm really excited about the speed of the development in that space, and I really think that once a couple of issues are solved with pins, due to their massive parallelized search space for the solution of the PDE, I believe they will be a lot faster and at the same accuracy with our classical solvers in the near future.
All right. Any downsides other than them being at their infancy right now? So when fully fledged, are they the perfect thing?
Well, at the moment, definitely not. The biggest downside at the moment is the accuracy. So these are not nearly enough as close to the actual solution as they should be when the problem settings get very difficult. So, said like there are still research ongoing to make them better. And the other issue with them is that you kind of have to train them on very expensive GPUs, which take a lot of computational time. Well, maybe they might be faster in clock time compared to the regular classical solvers. But if you compare the total computational effort spent on the GPU, I think they're wasting a lot of computational resources compared to CPU-based fast FEM solvers. Those are the main downsides of these methods.
I see. Well, you mentioned the other method that you sort of already almost went into the downsides of. So
Right.
so what are the upsides and indeed the downsides of that?
Right. Now, let's talk about those neural surrogates and their advanced versions of neural operators. So basically, the idea here is not to solve the entire thing from scratch by looking for a solution that satisfies the actual physical equations like pins, but to learn the direct output of physics equations from the training data directly. So the main difference of this compared to pins is that pins do not need any training data. They just need the boundary conditions and the physics equations of a problem. And they solve it per problem. For every single problem, you need to call pins from scratch, train them from scratch. And for neural surrogates, these basically learn from a massive training data. And they just basically learn to map the input space. Let's say it's like Cartesian coordinates, boundary conditions, type of the problem, the physics attached to the problem, and design parameters, etc. It can get any kind of input, and the output will basically be the solution itself. But these will learn from a lot of training data, and in the runtime, when they encounter with a new test case, you won't be training them from scratch like pins, trying to satisfy the physical equations or anything. But this will be just one input and output inference. So that's the main difference from pins. And the good thing about this is that it's extremely fast compared to pins. It's just one inference asset, and these also clockwise and computational efficiency wise faster than FEM solvers, especially for the problems that are really difficult. The downsides of these are, of course, these are heavily dependent on the training data. And training data is usually scarce, especially in numerical simulations. We don't have on the internet that much training data compared to, for example, the entire text corpora for training large language models. We don't have an equivalent as we speak for the physics, foundational physics models or anything. But one good thing about, maybe now we can talk about a little bit Quanscient. One good thing about Quanscient is that our main advantage is to be able to massively generate very diverse and a lot of training data for like a lot of simulations by parallelizing them on the cloud. This, in my opinion, is our key differentiator on training these neural surrogates, neural operators. And as of course, as you know, AI is very data hungry, and as much and as diverse training data we have, we sort of guarantee that it will be a lot better in the generalization during test time.
All right. How about just to circle back a bit? There was the hybrid option still,
Right.
And correct me if I'm wrong, but it was somehow different to either of these former ones. So
Right.
how does it differ as a method? And once again, what are the pros and cons of that method?
Right. Now, if you consider that the neural surrogates are, as the name suggests, are surrogates, so basically an approximations of the solutions not verified by the physics equations. But the power of them is that like we can quickly and in a somewhat dirty manner check a lot of design options with these. And we can take a few design options that we took out of the neural surrogates. Well, it's really difficult to do these with the classical solvers because they are slow, but we can do it very easily and very fast with neural surrogates. But what they miss is that these are approximations and should be verified. And now, after reducing the design options to, let's say, some sort of like K number of options that are probably correct but not verified yet, then we can actually run these simulations with a classical solver and verify that what neural surrogates suggests is actually holds with reality. So this is like how hybrid models would work.
You said would work. Does it mean that it's still not in use currently?
It's definitely in use. It's definitely in use. Maybe I should have said works.
All right. So sounds like a nice sort of combination of these both techniques. Is there any downsides to that then, other than the sort of downsides that were for both of them? So GPU access and data generation.
Right. Well, basically, the blocker here would be like if any of the neural surrogate suggestions, if none of them are actually as neural network predicted, then there's basically nothing the physics models can do. Like consider the case that like it came out with 10 to 20 different design options, and we tried to verify them with actual solvers, but none of them worked out. Then there's nothing you can do. So they still don't provide an exact solution, a guaranteed solution in that sense. So that might be the downside.
All right, and these were the techniques on the solver side. So, right. How about if we quickly touch on the sort of the engineering side or the other side with the large language models, for example? What kind of features or technologies are in use now on that side?
Right. Now, as you know, as in any other generative AI that works right now, there's a great hype around agents, AI agents. And for sure, a simulation agent, as we call, would be extremely helpful here. And the capabilities of such agent is in the simplest form, being basically a chatbot assistant to help the engineers in simple stuff such as documents search and understand the engineers how to use the product or the solver itself. So that would be basically something like ChatGPT, but super specialized in a certain solver. That's one thing, of course. The other thing would be automatize some engineering workflows. So, such as forming a geometry and filling some material properties. So basically, whatever you're doing, from importing a geometry to the solver until the point that you're getting the simulation output. So basically, everything that an engineer does in that period can be somewhat either assisted or automated by either large language models or a multimodal model. One example for this is something that we have also deployed is some anomaly detection, for example. We have seen some cases that some entries regarding the simulation were mistakenly entered wrong in the simulation environment, and it takes like multiple hours to run that wrong simulation only to end up with a nonsense result that you don't know why it happened. So basically, in such a case, we have a nice anomaly detection solution where basically prior to running the simulation, the LLM just checks based on our previous normal examples in our demo dataset and checks and understands whether the user might have made a mistake anywhere. Also, it raises a flag before actually running the simulation and saves the user of potentially many hours of wrong simulation.
What I'm thinking now is that is there a sort of comparison to be made in terms of meaningfulness between the solver side development with the AI and then the sort of let's say what do you call it when the engineers actually the sort of usage side utilization of AIs with these agents? Is there any comparison to be made there that which is more meaningful, which could have the more impact?
I think those are pretty orthogonal to each other. When you compare the engineering AI and the simulation AI, they are basically entirely different spaces. So the engineer's job is basically done up to the point of pressing the simulate button, and then the simulation starts then. So basically, I think they are like sort of non-overlapping and covers quite different spaces. And both of them are extremely meaningful, but maybe since the latter one, the simulation AI one, is sort of in a still research phase on it at some points, maybe the lowest hanging fruits are in the engineering AI side, I might say. But from a meaningfulness point of view, I think both have a very good potential.
Right. So in the future, in the near term future, we might see engineering workflows or software that have AI in either side or both of the sides. It doesn't really have to be either or both.
Totally agreed. Yes.
Right. So, well, if we look, let's say 3 to 5 years in the future, what do you see? Like, do you see fully AI-driven engineering simulation, or what is the role of AI in, let's say, 3 to 5 years in your best guess?
Right. I definitely see a lot wider adoption of these methods. Maybe in the beginning, at the solver side, a blend of AI-driven models and classical solvers. Maybe not entirely AI-driven models in the near future, but a blend of them, as we discussed, the hybrid models. And I think there will be a lot of focus on the verification of the AI-based models' outputs. either via mechanistical interpretability or explainability, or alternatively, a lot easier way is to just verify the results by running a classical solver. So again, in the simulation side, there will be a lot of hybrid solutions, in my opinion. When it comes to the engineering side, I think we will see more and more AI agents helping the engineers either form the geometry, define the material properties, maybe even help them with post-processing the simulation results in the ways that they want, or a coding assistance if they're using some sort of a code script based simulation tool like the one that we also have in Quanscient. And I also see, we haven't discussed about this before, but I also see some foundational physics models ramping up. So we already have a few powerful foundational models that are forming up nowadays, like either in foundational geometry models or foundational physics simulation models. I think they will just increase, and we might expect some similar trend to what's happening in LLMs right now. So more powerful methods, more training data generation, and maybe over time they will really become so good that we will trust them as we are trusting the LLMs right now in our simulations. But that's maybe not in 3 to 5 years, but let's say 5 to 10 years.
Well, broadly speaking, are there any sort of hard problems to solve, or any sort of major obstacles other than what we already discussed, being the access to hardware and data? Do those count as hard problems? So basically, are there any bottlenecks that are restricting the development of these AI or ML techniques?
Right. Yeah, apart from the stuff that we talked about, well, there is definitely room to improve in the neural network architecture space, because some solving physics equations are in nature quite different than the ones that we used to use deep learning, let's say for image recognition or some other recognition tasks or regression tasks. So as said, there are constantly some research ongoing. For example, one example can be the type of optimization algorithm you use when training neural networks. Now, there are a couple works that found out that the solution space of pins are not as easy as regular problems that we used to have in machine learning, and therefore they need some sort of second order Hessian-based optimizers. So these kind of things that either the neural network architecture or the optimization algorithm you use with them. So I think they still need some improvements. So there is some bottlenecks there. So the current technology we have seems not to be enough to easily solve this problem.
How about Quanscient-wise? You already mentioned a bit on the sort of key advantage, key differentiator. Could you just quickly summarize the sort of relationship of Quanscient and AI? Where are we now? What do we have, and where are we headed towards?
Right. We're currently working on a simulation agent, as I mentioned before, and we have actually already deployed some functionalities of that, such as the document search to help user questions regarding our platform, or how to use the platform, how to code with our scripting platform. We have also deployed, as I mentioned, the anomaly detection on having LLM double check the user-defined project properties, especially material properties, and raise an alarm if there's anything it sees wrong. And next thing we're working on is actually some agentic properties, such as the simulation agent having the help the engineer with geometry forming or defining material properties, etc. we are also in the simulation AI side. This was engineering AI side, and in the simulation AI side, we're also working heavily on neural surrogates that act as a fast and approximate neural solvers for some type of problems. We have already some nice experiments and good results on that space. And as said, the massive differentiating factor of Quanscient is we just don't rely on the readily available, publicly available simulation data sets out there, which are really limited in number, and we are able to massively generate whatever data set we want to train these models. So if you see, for example, these neural surrogates fail in some sort of problems, we can easily generate a new training data set for those spaces that we have not covered yet. So on that sense, I think this is it's really extremely important to be able to create your own training data. So imagine, for example, that OpenAI right now has a way to create another internet other than the one that's out there. So that's extremely valuable. I think that's the key thing that sets Quanscient apart from all the other companies out there.
All right. Well, I guess the final answer, or question rather, would be that is there something that you're personally excited about in the space, in the AI ML space, specifically in the physics context, that maybe isn't getting enough attention yet?
Well, it's certainly getting enough attention, I think. But what I'm particularly interested at is basically physics-informed neural networks.
Right.
So, well, I don't know. As said, like I'm basically a researcher and scientist at heart, and it's really fascinating for me to replace some 50-year old classical methods with these physics-informed neural networks. But as said, like they are still on rather, as you put it, their infancy, and we need to discover some sort of new architectures, new loss functions, new optimization algorithms to have them show the same impact of deep learning and neural network showed in other domains. But I really strongly believe that it will happen at some point.
Well, this was fascinating, and I think we could go for as long as we wanted to, but let's wrap it here. And a huge thanks for joining.
Thank you so much.
Thank you for listening to this episode of The State of Simulation. To stay updated with the latest episodes, webinars, blogs, white papers, and more, join our community of more than 7,000 engineers and engineer-minded people on our LinkedIn page, Quanscient. For more information about our AI research, visit our blog at quanscient.com/blog. Thank you again, and see you in the next one.